Okay, I am recording now, I think. Um, yeah, any questions before we begin? And I encourage interruption, please. Otherwise, I'm gonna feel like I'm talking to myself.
So how do you import the zip file into this format?
Sure, yeah, I can go over that. So, I mean, let's just say I didn't have this, right? Or let me just delete up to the comment. So, boom. So right now what I'm looking at is just in fact, let me full screen this so it's a little easier to see. Right now what I'm looking at is basically like what you'd have for any Topaz file. So you load the data here. So this is the string that tells you what the file name is. And then you're always going to have some sort of background, which is this line here. Here I have basically a polynomial that's fitting the background, and that's just 7 coefficients. And so you could think of this as like x to the fifth power, x to the fourth power, x to the third power, x cubed, x squared, a linear term, and then a constant background. I'm not exactly sure if that's left to right or right to left, but that's the idea. It's just a polynomial. And then you're going to want to have this like wavelength line, which basically tells you the wavelength of whatever radiation you're using here. The neutron happen to have 1.54 angstrom wavelength. You could look up what these other things mean. I forget what they mean, but L naught is the wavelength here. Here I'm specifying that it's neutron data. Um, you need to specify this if you're working with neutron data, otherwise it won't give you the right form factors. Everything will look kind of wonky. And then this Lorentz polarization factor, neutrons, I guess if they're unpolarized, which they are in this case, this should be 90. Um, Same thing for X-rays. If you're using unpolarized X-rays, this should be 90. So after we have all that, we can import the CIF. And I should say Topaz doesn't really care about indentation. So the only reason I'm indenting this is to make it look nice. But things can be, the white space in this like document really doesn't matter. So to import a CIF, what we're going to do is we're going to go over here into this like macro column in JEdit, and we can open up. Um, I guess I'll tell you what these are. So the Durham menus are like tutorial menus. So it has a little bit more structure to it. But with that being said, it's a little less flexible. So if you want to do like a very basic, like starting from scratch type of thing, you can start from these menus. And if I, for example, select a data file here, this isn't like a file, even though it looks like folders and files. These are actually commands. So if I click on this, it's going to run a command. So if I click select data file, it's actually going to open up basically another one of these files and basically start me from scratch and ask, where's the data? And then it'll set all this template up for me. Um, so the Dura menus are like, yeah, they're like little all-in-one commands. In this version 6 menu, or equivalently version 4 and version 5, those are like a fuller set of commands, but they're less user-friendly. But we kind of want to use those for right now. It offers you a little more flexibility, and you could get a lot more specific tools in here that you can't access through this tutorial-like menu. So what we're going to do then is we're going to look through these folders and we're going to say, okay, we need to import some sort of structure. So I'm going to look in this folder. And one of the tools you have here is you can insert a CIF in input format. So I'm going to move my cursor to where I should put the CIF, which is sort of below the data. And then I'm going to double click this and you see it opens a window. And I'm going to go look for the CIF file of the compound that we're going to be analyzing today. So for today, it's lanthanum manganate, LaMNO3, where the manganese is magnetic. Here in my folder, which is on the D drive, you'll be able to find this folder called Magnetic Refinement Tutorial. So all of you should have access to this, right? So you can just open this up and get the files that we're working with today. Uh, Inside this folder, I have the CIF file, which is the PNMA structure of lanthanum manganate. So if I open that, basically it spits out the CIF file, but in the format that Topaz likes to read. Okay. A lot of times when you do this though, let's say you're on ICSD and you download a CIF file and you want to import it, the CIF file is not formatted in a way that Topaz likes to read. And so it'll be missing the space group. A lot of times it'll be missing the angles. And in this case, it's also missing some other things that we need to add, like peak shape and overall scale factor. So just because you import the CIF doesn't mean that it is done and that you can just run it. Um,
Does it matter in which order you import the CIF file or the data files?
it does not. It does not.
Okay.
So if you have like multiple phases, you can import them in whatever order you want.
Okay.
I think the order does matter in the sense that like you need to specify what data you're looking at before you start telling it which sifs to use. So you can't have this whole structure block, the STR, this thing. You can't have this whole block above the X-ray diffraction data block. So this
Oh,
usually
okay. It
sits at the
has to
top.
be right below it.
Yeah, you usually, I guess, are working with one file, right? So it's usually you t tell it what the data is, and then you tell it all the structures in that data. But you can also co-refine multiple data sets. So I could have another data block, and I could have other structures under that belong to this data set, the second data set. But that's a little advanced, and it's not pretty common that you're going to do that. But for example, you could co-refine X-ray and neutron data at the same time.
Okay.
All right, so now we have our structure imported. Um, I'm gonna, add in the things that I notice are missing. So one of them is a scale factor. You see that I type in the word scale and it turns blue because Topaz knows what that is. And then I'll just give it a default value. Let's just say 1.0 to start. Um, and in Topaz, I want Topaz to decide what that scale factor should be. Um, I'll come back to that in a second. The other thing I need is a peak shape, but I'm actually not going to include that for now. Let's just look at what this looks like with, a minimal working file. So once I have this ready, I can just hit this save set button, and that will basically send this file to Topaz. It'll let Topaz know that when it starts up, it should be reading this file, and you can see that it says input output complete down here, disappeared. And then once I have that done, I can start Topaz by clicking the TA button. Okay, and now you can see it says launch mode. It's running the file that I was just working on in JEdit. And I could do one of two things now. I could run a single cycle by clicking this step button, or I can run many cycles by pushing this run button. And for the sake of right now, I just want to do one cycle. So it works. So if you see data pop up down here, that means your file is good enough to run something. And so if I zoom in here, controls are a little finicky when you're on a remote desktop. The red curve here is the fit. The blue is the data. So it's showing the data up here, but it's also showing it down here. And then the gray is the subtracted difference between the data and the fit. Okay, so right now, my fit has these really, really huge peaks, but pretty, my data has a much different scale than the fit. Okay, and this is because I told Topaz the scale for the simulation should be 1.0. And in fact, this is actually a really huge number for Topaz. So what I want to do is I want to let Topaz adjust that number on its own. And so I stopped the refinement, and I'm going to come over here and tell Topaz, I want you to adjust this or refine this value as we go along. So for that, I'm going to put a little at symbol in front of this number, and that tells Topaz I want it to refine it. So now I don't have to open Topaz again. I can just keep this window open, but I do need to save this file. If I don't save it, Topaz won't read the changes that I made here. So now that I've made that change, I can let Topaz run, and you see it's going crazy because it's adjusting not only the scale, but also the background. So I've stopped the refinement, and I think it kind of blew up, but it actually is, if we look at what it's done now, it's actually adjusted the scale so that it looks a little bit more like the scale of the data. And we can go back to our JEdit file. Oops, I rejected the final solution. So let me run that again. So it's going to ask me, do you want to update the input file with the values that it found? And if you like the fit, if you think the fit is better than it was before, you hit yes. If you don't think it was better, you probably want to hit no, and it'll save basically the starting point that you gave it. Here we're going to overwrite what we put in with the results. We're going to hit yes, and then we go back over here, and JEdit says, hey, something changed in your file. And sure enough, the scale factor went down, right? Scale factor went from 1 to 0.001. Okay. So right now, you see that the peaks that I'm simulating are really, really narrow. They're basically like delta functions. They're just little like, needles. But the actual data is these much broader peaks, right? So if I look at every single peak has some width that's larger than what I'm simulating. And that's because I haven't told Topaz what peak shape to use. There are 3 peak shapes you can use. So if we look, I think also in the structure folder, there's a peak type folder within that, and you can choose a pseudovoid peak shape, this TCHZ peak type, which you could look up what that is. There are 4 different names of people. And then a pseudovoid 2, the sequel. I don't know exactly how these are different, but you can look up in the Topaz technical reference. It tells you the details about what all these are. For our case, I think we can use the pseudovoid peak type, and that should be good enough. I should say also you can use things like crystallite size broadening. So just like a simple Lorentzian peak shape or a Gaussian peak shape, that's what these are. Um, in fact, I think I've tried all of these, and for this data set, the crystallite size Lorentzian peak shape gives us the best fit. So I might actually use that. So if I double click this, it's going to insert a line uh, on the line where I was hovering with my cursor, or where the cursor was sort of sitting. It's going to insert the text wherever I was. So okay, now that I've added that peak shape, you see that there's some like variable here, and I'm refining that variable because I have the at symbol in front of it. So that should allow me to refine the peak width. So now if I run it, you see that Topaz eventually reaches some sort of nice solution. Okay. And if I go back to my data or my input file, I see also that it has adjusted this parameter. Cool. All right, so just to recap what I've done so far, I've told Topaz what my structure looks like. So I've told it where the atoms are. If I look at the structure, it knows, oh, sometimes this doesn't work. Yeah, it should show me a nice little structure there, but sometimes it doesn't. Let me try, I think if you type view structure, that might work. Yay, okay. So it knows where all the atoms are, but it has no idea about any magnetism, okay? So what's happening here is it's fitting all the peaks that correspond to the atomic positions, but it's not fitting any of the peaks that correspond to any magnetic order or magnetic correlations. So there's 2 ways we can go about fitting these reflections that are missing, and both of them are what we call symmetry mode analysis. Any questions before I continue on with that?
For neutrons, do you find for doing neutron data, do you find like because I know in all of the X-ray data we usually use the TCH. So for neutrons, do you find it better to just let it do like Lorentzian fitting, or is it
To some degree, it doesn't really matter. I think unless you're like trying to extract some very careful information from your peak width, you probably
Mhm.
just want it to get like a decent fit. So you could play around with whichever one fits better. Um,
Okay.
if you look through like tutorials of people fitting neutron data, people use a variety. You could get away with a pseudo void, and your R squared will be like 1 higher. It won't be that big of a difference.
Okay.
Yeah. It also depends on the instrument, right? I mean, depending on how your instrument's working, it might give you a different peak shape that might be more similar to Lorentzian or more similar to a Gaussian. Who knows? Why that is sort of beyond me. Good question. Anybody else? Okay. Um, so the first thing we'll do is we will use what's called Sarah, which is this program right here. It's like symmetry analysis, represent symmetry something. I should look it up. Sarah representational.
Yeah, it actually just stands for me.
Yeah,
It's
simulated annealing. Yeah, simulated annealing and representation analysis. Okay, what is the H for? Who knows? Um, so this tool, they have a web version that works for full prof, but in order to use it with Topaz, you have to download the software. So there's two software things. One of them is Refine, and the other one is the representational analysis, and use them in order. So that you use the representational analysis first, and then with the output from that software, then you feed that in to the Refine. So we're going to open this. Okay, and this is what it looks like. And basically, what this is going to do is it's going to tell us all the ways that we have uh, to break the symmetry um, using magnetism. Okay, so it's going to start off with the space group of the structure that we gave it. And it's going to basically look at every single way. If you've taken group theory class, this might sound familiar. It's going to look at every single way to break that symmetry. So the steps here are first, you're going to enter the space group. So we're going to go to define parameters over here. And then we're going to look through this list for our space group. I believe it's 62. Yeah, PNMA. So I'm going to select that. And then I'm going to hit OK. The second step is going to be to enter a propagation vector for that's this K vector here. So I'm going to click that. For most magnetic systems, the K vector is probably going to be 0, 0, 0, meaning that the magnetic unit cell is the same as the structural unit cell or the nuclear unit cell. Of course, there are cases where that's not going to be the case, but in general, I think when you have a compound that, let's say you measured it and you don't know what the magnetic structure is, and you sent it off for neutron diffraction, you come back with some magnetic peaks. I think the first thing to try is a Q equals 0 order. So in general, we want to start with this, and then if it looks like none of the Q equals 0 orders work, that's when you set up a meeting with Steven and say, hey, what do I do? Luckily, I've never had to run into anything more complicated than the Q equals 0 so far. So this works most of the time. So I'm going to hit OK, and then the third step is to enter the atomic positions, and here we're just going to add the atomic positions of the magnetic atoms. So in our case, our magnetic atom is manganese, and then we have to enter in the coordinates. So let's look at what those coordinates are. Could look either at the CIF file or can look here, and it looks like the manganese is at the origin. So I'm going to go back to Sarah here. I'm going to put in 0, space 0, space 0. Okay, and then I hit add atom. Okay. And then we hit calculate. Okay. And this is going to take a long time, so I'm not going to run it. Hopefully it didn't overwrite the file that I already gave it. But basically, yeah, you hit this, and then it'll just sit there for maybe like 5 minutes, and it'll spit out some files. Okay, so I'm going to close this, and hopefully it didn't overwrite the files that I already generated. So let's go look for those files. So those will be on the C drive of the computer. It'll be in program files 86. You have to scroll down to the Sarah folder, and it basically spits them out inside, I think, well, where is it? Maybe it's in program files. Maybe I just shot myself in the foot. Damn. Hmm. Okay, how about this? We will let that run, and then while that's running, I will show you how to do it in ISODISTORT, which is the other symmetry mode analysis software. Okay, so real quick, I'm just gonna start this up again. Okay, then I'm gonna calculate. I'm just gonna use whatever it recommends. Okay, and it says, please be patient. This may take a moment, and it really does. It really takes a long time. So we'll come back to the Sarah method in a second. So let's now look at how to do it using ISODISTORT. So ISODISTORT is a web-based software that basically does the same thing that Sarah does. Okay, so it's going to tell you all the ways that you could possibly break the symmetry. So I type in just ISODISTORT in Google. It's this one right here. And what it's going to ask us for, it's going to start ask us for the CIF file. So I'm going to go ahead and feed it the CIF file that we started with. Okay, and then hit OK. And then it takes us to this page, which is going to give us a bunch of options of what to distort within our structure. So you can use this for displacive transitions. So if you want to, you see some new peaks arise that you think are from atoms moving off their nominal sites, you can simulate displacive distortions. You can also, I guess, nominally simulate occupational disorder or distortions. Sort of less clearly defined for me what that is. You can do rotational distortions, strain, but here we just want to check this box. We're only going to choose the distortions of manganese magnetic degrees of freedom. Okay, so once I just choose that I want to consider manganese magnetic, I hit change. Okay, and that updates the whole page. And then I think the easiest thing to do is to go to method 2 here, which is looking at the specific wave vector, which is sort of analogous to what we just did in Sarah. We can choose different propagation vectors. As you can see, there are many. These are basically different ways of enlarging the unit cell. Here, we're just going to stick with k equals 0 or q equals 0, which is the simplest case. And we can go ahead from there. There are other things you can do if you kind of know the space group symmetry of what your magnetic structure should be. You can choose it here. And then I guess this is kind of cool. If you have a CIF, for whatever reason, if you have a CIF that's already distorted, so like let's say I have a parent CIF and I have a CIF that is lower symmetry, I can feed it in here and basically get all the distortion modes out. It'll automatically tell me. So that's kind of cool. That's useful in some cases. All right, so we're going to go ahead with method 2. Hit OK. And then you see it gives us 4 different options of irreducible representations, or IRs. And these are a fancy way of saying there are 4 different ways that I can lower the symmetry from PNMA to something lower. In our case, I already know what the answer is. I know it's M gamma 4, which is the magnetic gamma point, the 4th option. All of these other ones will give you different magnetic orders, and it's wise to try all 4 to see which one works the best. Okay, that's sort of the workflow for ISODISTORT. As we'll see in the Sarah method, it's going to give us all 4 at the same time, and we can sort of refine all 4 at once and see which one looks the best. But here you kind of have to go one by one. So I'm just going to jump straight to the answer, which is the M gamma 4. And then I hit OK. And it gives me this order parameter direction. There might be more than one option for this as well. Probably want to try those. But here, luckily, we're only given one. All right, so that takes us to this page, and this might look like a lot, but really you just want to look at these little radio buttons here. So one of the cool things you can do is you can save an interactive distortion. So if I just hit OK, it gives me this little ISOVIS file. And so if I open the ISOVIS software on the Quantum Foundry computer, you can just download this on your computer as well. I can open the whatever file I just downloaded, where is it? Yeah, it's here, right? ISOVIS. Okay, let's go to downloads. Okay. All right, so here's my structure with all the atoms. And here it says manganese modes, right? So these are all the magnetic manganese modes. So I can turn these on as little sliders and you can see what the different magnetic orders might look like. So this is one parameter. This is another parameter. And this is another parameter. And you see that like all of them are in different directions. And you might have a superposition of multiple of them. So this should give us enough degrees of freedom to capture any sort of magnetic order that would follow, I guess, what I might call naively the rules of symmetry breaking that are allowed in this gamma 4 irrep. Okay, big words, I know, but I think the visualization helps. Okay, so this is basically what we're going to let Topaz refine. It's going to play with all of these until the magnetic reflections look like what they are in the data.
Are any of like the distortion modes like the same just from a different like perspective? Like you should have like some of them are any of them like degenerate or does that like matter if you come at it from like I don't know. If you ever run into that problem like of them being like the same.
If I understand you correctly, you're saying like if I have magnetic order along, let's say I have a cubic cell, I could have
Yeah.
magnetic order along A, I could have magnetic order along B, I could have magnetic order along C, and all of those should look the same, right?
Yeah.
In a powder diffraction experiment, you can't really resolve between those, right? But the uh, symmetry analysis here will take that into account. So it'll only give you really one mode, I think.
Okay.
Um, yeah, and here you notice like it gave us three different modes. It gave us sort of like I guess.
Hi, Steve. It's Lillian.
Oh, hey, Lily.
Lillian heard you in the QF office.
That's funny. Um, so yeah, one of these modes is going to be in the plane, right, along, let's say A, I think. The other mode is going to be along B, and this other mode is like out of the plane, right? And
Mhm.
it's giving us all three of these because I think they're all not degenerate because this is not cubic. This is actually orthorhombic. So A, B, and C are all different. But yeah, I mean, you might be able to feed it like a cubic cell and see what happens. I think it should just give you one mode. Okay, that's a good question though. I mean, it's worth testing. People have different approaches with this. I've heard conflicting things. Uh, if you do have like three degenerate modes, it's like some people say, oh, you should just refine one. Um, but I don't really think it matters. Um, yeah, Topaz
I've
should be
heard from
smart.
Steven that it doesn't really matter, or like that's Steven's opinion.
Yeah. It doesn't really matter. I've also been told by like beamline scientists that like, oh, you should only refine one, but I don't know. I think it's more of like a picture of like intuition. Like you got to look at it, say like, does this magnetic order make sense? Um, and you'll also see the coefficients of all three of these modes. So if like, let's say that one is like 100% and these ones are like 10 and 10, you might you might just say, hey, this is the only mode that's really strong. Maybe these other two components aren't actually important. Okay, so we'll see that in a second. Okay, now for the actual refinement. What we want to do is we want to select the Topaz structure file here, and then we hit OK, and it's going to spit out basically a structure that we can copy and paste into our input file. So let's open that up, see what it looks like. So let's grab it and put it in here. Okay, so this is what it looks like. So for this method, when we're using ISODISTORT, we're gonna ignore what we already put in. So we're not gonna use this structure here. We're basically gonna copy all the information from this guy into the one that it gave us, because it's basically, you know, it has all the lattice parameters and the scale and stuff on its own. So this is what I'll call this is combined nuclear and magnetic refinement. Okay. With Sarah, we'll do them separately. With Sarah, we'll get a phase on its own, or a structure on its own that is just the magnetic component. Here, they're sort of intertwined. So that's maybe a setback of the ISODISTORT method. So to orient you on what we're looking at, this is the standard structural information. This is the lattice parameters. This is the scale. We still need to add a peak type. So I'm going to go ahead and add a peak type again. And then everything basically below this is going to be the magnetic modes. So I think there might be some things that won't run here. It's worth checking. Actually, I think this is all good. So these are all our atomic sites. And you see manganese has this added little guy right here. And these are the magnetic components that sit on the manganese site. So this is the magnetic vector along X, along Y, and along Z. And you notice these are all calculated, and these are calculated all the way through these equations from the coefficients that sit right here. So these are the coefficients that we're going to refine that basically control the strength of the magnetism. It's also helpful here to put in this keyword here. So these will show us in Bohr magnetons the projection of the magnetic moment. So it'll just, you know, flat out tell you how big the magnetism is, or the ordered moment. But these two macros are different. So this one will tell you what the projection of these magnetic moments are along A, B, and C. Okay, so those are the crystallographic axes. And those may not be the same as like X, Y, and Z as we're used to thinking about in like Cartesian, right? So you should put both here. This is especially important if you're working with like a hexagonal cell or something that doesn't have like at least orthorhombic symmetry. In our case, this is orthorhombic, so both of them should be the same. But more generally, you basically want to look at this because in the Cartesian world, you can calculate the total magnitude of the moment by just saying x squared plus y squared plus z squared, just like we're used to calculating the magnitude of a vector. You can't always do that if your vector components are not 90 degrees apart, which is what this would give you. So just be careful. Make sure you're calculating the magnitude of your moment using this function. All right, so the first thing we're going to want to do is we're just going to run this to see if it works. Okay, so I'm going to save that. I'm going to open TOPAS back up, and I'm just going to let it find a good nuclear solution. Okay, so it looks like that's good enough. And then I'm going to go back here, and I'm going to allow it to refine all three of these modes. Okay, so these are all three modes that belong to this IREP. So generally, you don't want to refine one of these at a time. You want to look for all the modes that belong to a shared IREP. So in this case, all of them belong to gamma 4. And then we're going to allow all three of these to refine. Topaz also basically requires you to give it a little nudge away from 0, because 0 is sort of like a metastable value. So it'll just sit at 0 if you don't give it a non-zero value. So we're going to give it some like very small nudge away from 0, and then it should kick it into action. So let's go ahead and refine that. And you see it's already starting to capture the magnetic reflections, right?
To refine it, you also don't have to add another at in front of it, or you just leave it as a number.
It's a good question. So in Topaz, when you have a variable that has no name, like scale, right, you can just throw an at symbol in front of it. Or if I give it a name, I could say, my scale factor and go like that, right? And then it'll still refine. So it should still be refining the scale. To stop refinement, when it has a name, I don't want to delete the name. Instead, I'm going to put a little exclamation point in front of it. Okay, and that's what we saw here. This is like a variable mm1, mm2, and mm3, and they were turned off. And so I turned them on by deleting that exclamation point.
Oh, okay.
Good question.
Thank you.
All right, so we see that the coefficients have refined, right? And we can scroll down and look at what our magnetic moment is. And it looks like it's something like this, which looks a little huge. Something maybe doesn't seem quite right. Background. And keep refining the scale factor. In fact, I have a solution here. Why don't I just look at my solution? I think it's actually okay. All right, so basically what this is telling us is that the magnetic moment mostly points along X. It has a small Y component, and then it has a very small Z component. And you could calculate the magnitude of the ordered moment, but by just calculating the norm of all three of these. Okay, and then to visualize this, we can actually go into the structure here. And I think you just right click and hit view structure. And it should show you the magnetic moments. It might actually not in this mode. It might only do it when we're looking at the Sarah version, but I think if I refine it, you should see the magnetic moments dancing around. Yeah, okay. You see them? It's like, I guess it's not converging quite well in this refinement, but let me stop that and start it again. So you could visualize what it's doing to the structure here. So we could kind of see what's going on. The magnetic moments are kind of pointing in the plane. They have a small Z component. And it's sort of like this A-type order where the layers are ferromagnetic, but then each layer compared to the next layer, it looks anti-ferromagnetic. So they're reversed. So this layer down here is all pointing to the left. This layer here is all pointing to the right. And then the layer on top is all pointing to the left. We should be able to get R value that's like 3 for this data. I don't know why that's not the case here. Let me try. I'm going to try to nudge it again. I definitely got a better fit last time. Let me look. I guess I used a PV peak type pseudovoid. Let me try pseudovoid peak type. I'm going to comment out my old peak type and then I'm going to add in the pseudovoid. Okay, let's let that try to figure it out. Doesn't seem to be much improved. Well, okay. In the other version I did on my own time, I got an R value of 3.9. So you should be able to at least get the 3.9 here. Right now we're sitting around like 5, which is not the best. Oh, I know what it was. I think it was the thermal displacement parameters. Let's go over here. Yeah, okay. So this is something to note. So when you use the ISODISTORT method, it basically erases the thermal displacement parameters. So you want to add those back in from your CIF file. So here's what they were in the CIF file. And once I add those in, the fit should improve quite a bit. So I'm just going to use the same value for all these guys. Okay, and now when I refine it, it should, yeah. And so now our value went down to 3.9. And interestingly, right, the magnetic moments have changed a little bit. So they have a lot less component along Z. They're really in the plane now. So it's really important that you get a very good nuclear fit before you start to do your magnetic fit. So make sure everything is spick and span with your atomic positions and your thermal displacements and stuff like that. Otherwise, your magnetic structure might lead you to some false positive results, okay? All right, let's see if Sarah is done cooking. Okay. Any questions on the ISODISTORT stuff before I move on? No? Someone say something.
Very good.
All right. All right, now looking at the Sarah method, we're done with the representational analysis part. Now we're going to open Sarah Refine. Okay, so it says, two steps. Use one of the menus. You can do GSAS, full prof, or Topaz. Here we're going to use Topaz. So you basically just follow these in order. So we're going to open the Sarah mat file, and then it's going to prompt us to open our Topaz input file, and then it's going to help us edit it. There is a problem here, though. You cannot have your input file in a directory that has spaces in it. So I'm going to take my input file, which is, where is it? Here. Yeah, here's my input file, right? I can't have it in my folder because my folder has a space in between my first and last name. So I'm just going to throw it on the desktop for now. I'm going to replace the file that I already had there. So we're actually going to modify it on the desktop to avoid problems. So we're going to load in the matrix file, which is the one that lives in the C drive. So let's go C, program files x86, Sarah. Okay, and then we see that there's some matrix files here already. It's numbered by space group. So you see I've already done some refinements for other compounds. This one's for the 133. This one is our PNMA. Okay. So we're going to open that, and then it's going to immediately tell us to open our Topaz input file. So then I'm going to go to the desktop and open up our tutorial file. Okay. So you see all this stuff that it shows you, right? Like basis vectors. And what these are going to do is it's going to lower the symmetry in the way similar to what we saw in ISODISTORT. But all of these are grouped by their irreducible representation, just like they were in ISODISTORT. It's a little harder to see here, but you see this one's gamma 1, gamma 1, gamma 1. This one's gamma 3, gamma 3, gamma 3, and so on, right? Gamma 5 and then gamma 7. They're grouped down here. So if I want to, select just one, I could do that, and I just hit select, and it automatically selects the basis vectors that correspond to that. But usually this technique is powerful enough that you can select all of them at the same time, and then we're going to refine them, and it should just give us whichever one is dominating. So I'm going to go ahead and select all of them, and then you can do two things here. You can say, select the magnetic phase inside your input file for editing. This never works in my experience. So if I click it, it's just going to say, I can't do it. And then it's going to switch to this other mode where it just gives me a magnetic phase. So this is, maybe a drawback if you wanted to use the other method, but if you wanted to do a combined magnetic and nuclear refinement, but actually I think separating the magnetic contribution from the nuclear contribution is actually pretty useful. All right. So this is basically a structure. I'm going to take it into Topaz. Let me make sure that I'm looking at the file. Actually, I don't really need to use the one that's on the desktop anymore. I could just stick with this one. So I'm going to delete everything that I just did for ISODISTORT because that's already saved in a different file. So I'm going to delete up to here. I'm going to turn this guy back on. So this is the nuclear phase that I had earlier. All right. And then now this part down here is just going to be the magnetic phase, magnetic structure. So I'm going to paste all that in. This is all that Sarah gave me. All right, so whatever Sarah spits out is usually really, really crappy. It's like full of typos and like incorrect syntax. So I will basically go through and show you what needs to be fixed. But there's so much to fix that maybe I'll just show you a file where everything is already fixed. So this magnetic BV is actually supposed to be the phase name. So you can call this, I don't know, LAMNO3 magnetic. Okay, it has to be a string like that. We need to add in the scale factor here, and the scale needs to be the same as the scale factor for the nuclear structure. So I actually will give this a name. I'll say, my scale factor or something like this. And then I can basically use that to inform my magnetic structure. So the scale here will be equal to my scale factor, and then I end the equation with a semicolon. Okay, and actually I can print out what the value is by using a colon and then putting a number here. The number can be anything. It'll just print out whatever this equation evaluates to. So I'm just gonna put 0 for now. And then we need a peak type. Normally, I mean, you don't expect necessarily that the magnetic peaks will have the same peak shape as the nuclear peaks. So I'm going to add in a separate peak shape for this phase. Also, let me just fix the indentation a little bit so that it looks nicer. What else? There are other things like these equations don't have a semicolon at the end, which they need to have a semicolon. You can't have in Topaz a plus and a minus next to each other, so you need to go through and replace all these pluses with nothing. So that's annoying. You have to go through and do all of that. Then at the end of these equations, you also need semicolons. So all of these need a semicolon. Don't hate on Sarah like that. I just saw the chat. What else? Oh yeah, even crazier. None of these are used. So this whole block of code is just a waste. And then all these variables don't have the right parameter keyword before them. What else? Are there any other errors that Sarah gives? Oh yeah, so it says MM display crystal axis is actually MM crystal axis display. So you can imagine this is a nightmare. I had to figure out all this by hand after reading through all the documentation. So that was annoying. This actually is incorrect syntax. You can't have the same variable name defined more than once. So I'm just gonna give it like a default variable name, the @ symbol. So anyway, you have to fix all those errors, and then even then, like there's other stuff like this is supposed to be a comment, not a tilde or a little tick mark. So anyway, you can just open my sarah.inp file, and you can basically play like find all the differences between these two pictures. You could look at your output from Sarah and look at my, working version and use this as a reference for like what's missing. But hopefully that guides you to where you should look for like mistakes that Sarah spits out. All right, so this is a working version. I'm just going to reset all these back to 0 so we can see what we're dealing with here. There are two ways to approach this. One of the ways is you can go through and refine each irrep by look one by one. So here's all three basis vectors, basis vector 1, 2, and 3 for irrep 1. So this is gamma 1. So what that would look like is I'd take this guy. Ooh, wait, actually, I realize there's an error here. I need to keep the same scale factor. This should be equal to the scale factor from the nuclear phase. Okay, so I could let the first irrep refine and then see how good of a job that does. So let's in fact do that. So because this is a new file, I'm going to close Topaz. I'm going to reload Topaz where it's launching from the file tutorial_Sarah. And you see what it's doing here is it's trying this type of magnetic order. And let's see if it does a good job. So let's stop. And okay, this does an okay job. It fits this peak, but it's also like missing this peak, and this peak is too high. So this order is decent, but it's not doing a great job. So let's look at what this order is. It's kind of hard to see where the magnetic moments are, huh? Oops. Come on. I believe you could change the transparency of the atoms here so you can see the moments, but I forget how to do that. Oh yeah, here we go. Transparency. Yeah, so the moments here are like, I don't know if you can see them, but they're little arrows that are hidden inside the atoms and they're pointing like out of the plane. They're kind of diagonal. And that's not really what we expect. Okay, from the ISODISTORT solution, we already knew that this is going to be some sort of in-plane order. And also the peaks don't match, so right away it's like a lot of red flags. So I'm going to set these back to 0. And I could basically go down the line of all of these different irreps. And I could try, say, gamma 3 next, which is these. And then I'll try gamma 5, and then I'll try gamma 7. And I already know the answer is going to be gamma 5 here. So I'm going to try these three, the basis vectors 7, 8, and 9. And if I refine that, okay, we see that I think it's this one. Maybe I'm wrong. No, it's doing pretty good. The R squared, like the best R squared is like 3.9, which is comparable with what we got from ISODISTORT, right? So yeah, this is doing a great job. This fits all the peaks very nicely. And I can go look at the magnetic phase. Oof. Okay, never mind. What is it doing?
Maybe it didn't update the
It
view.
feels like it did an update, yeah, because this looks right. These values look right. Let's try that again. Yeah, okay. This looks more right. So in plane, ferromagnetic order, out of plane, antiferromagnetic. Right? Same result that we got from ISODISTORT. Okay, oops, it keeps getting stuck. You should also be able to rely on Topaz to just tell you which one is the best. So I can actually, in the best case scenario, I can basically let all of them refine at once. So let's just set these all to 0. I will say that in this code, you don't need to give it a nudge because it has this parameter value on continue. So as soon as it tries to refine, it'll start with a random value between -1 and 1. So that's why I'm not making all of these 0.01. I'm just leaving them at 0 because it'll automatically nudge it. So that's kind of nice. But let's see, if I refine all of these, we should just see 7, 8, and 9 are the biggest. So yeah, right away it finds solution. And what does it say? Everybody's basically 0 except for this guy. He's huge. So what I would do then, if I was doing this from scratch, is I would comment out everybody except for the irrep where I found the biggest number. So that's the irrep 5, right? So I keep 7 because it's big, but I also keep its siblings 8 and 9. Okay. And then I want to set all these other ones to 0. And we basically end up with the same situation I had when I was trying all of them individually. Okay. We get a good RWP, which is like 3.9 again, I think. Let's see. It's up here, 3.9. And yeah, here's our moment. And with 30 seconds to spare, that was my magnetic tutorial. questions, comments, concerns?
Nice.
Nice. All right. Well, yeah. Let me know if you have any other questions. Otherwise, I'll stop the recording. How do I stop the recording?
Oh, I had a question from
Yeah.
ISODISTORT.